Hey guys.
Okay. So just a quick question: when is the final report due?
It's gonna be due May 23rd, and so not this Sunday, but the Sunday after that.
Okay.
Mhm.
Also, well, we're based like more or less on like when I went back to my the project, I realized something else
Mhm.
that like because of like the top part of the sphere on the chest piece or something, I'm not sure if that would make sense to like simulate like like I was thinking, oh, I'd have it be a cylinder that has the same radius as the smallest part of the piece or something.
Yep.
But it does like the top of the circle does go to a point or something. Like it's like infinitely small or something at the very top or something. Like
Yep.
so I think that would make sense now that I think about it.
Yeah, I think that makes a lot of sense too. I think that'd be a pretty good representation of your geometry.
Yeah, but like the plan was for a cylinder or something, and like for the circle part, it goes to like a point, like it gets infinitely small basically.
Yeah.
So what radius would I be using for the cylinder? Because it does technically like the shape does technically go to a point or something, so it does get like infinitely thin basically.
Right. Right. I mean, can you just make it like can you create like a I can use the revolution tool in SolidWorks where you kind of make like the cross section kind of go up to a point and then just revolve that around like that to make your cylinder.
Um, like I was thinking more not like actually going in and changing the model, but like just doing pen and paper work or something. Right.
Oh, just pen and paper work. I see. And so, so you're going to plug into an equation that requires a radius, and then right now your radius, you're saying that you're not sure what radius to plug in because, you know, because your pieces are rounded, and so at the top it kind of goes up to a point just like that, which is
Yeah.
technically a radius of 0. I would choose probably the like you know you have your kind of spherical thing on top of your on top of your on top of your chest piece, right? And so you have the radius of that sphere. I think if you just take radius divided by 2, which is I think the average radius across that entire thing. So if you go from one end of the sphere to the other one, on average, the distance you are from the center is going to be radius divided by 2, right? And so I think if you choose that, I think that's that's probably a good place to start.
Okay.
Yeah.
Well, thank you.
The exam? Oh, did we not talk about that? Oh, I guess, yeah, because I just finished it on Friday. So let me see. I forgot already. So the average on the exam was about a 33. No, sorry. Let's see. What's 77 divided by 2? Average on the exam was about 38.5 out of 50, and so about a 77%. Yeah. Yeah, it was a tough exam. Oh, I need to upload the solutions too. All right. I'll do that. I'll do that tonight.
Hmm.
Okay, it's 4 o'clock, so let's go ahead and get started today. All right, good afternoon, everyone. How's everyone doing today?
We're almost there.
Almost there, that's right. Yeah, 1 more week to go. So we have 2 more class sessions. And so this week, relatively chill. And so today, we're going to be going over how to set up fluid mechanics simulations in ANSYS. So for those of you who are interested in CFD, computational fluid dynamics, this should give you at least, a first step. And so, of course, it goes a lot deeper than this. You can take a whole class in CFD, but, you at least can get started with that, okay? And then Thursday, I was able to secure a guest speaker for Thursday. And so Thursday, I have someone coming in. I actually don't know who it is because it's being set up by the department. But he's supposedly a professional engineer. He's worked for a lot of years, and he's used ANSYS a lot in his professional work. And so I've asked him to come and speak just on how he uses ANSYS, kind of his kind of general approach, and how he how he goes about solving things. And I thought that would be a really valuable thing to kind of end the class with, so that because I know a lot of you guys are going to be, a lot of you guys are graduating after this week. And so to get that perspective of, how the stuff that we learned in this class can be used in industry, I thought that would be kind of a nice way to end. And so I'll send an email just to remind everyone. So Thursday should be really interesting. It's actually something I'm really interested in learning too, because I've actually only really had finite element experience, at least in my own work, just in research. And I've heard things about industry, and I've tried to incorporate that stuff into this class. But to hear someone talk about that stuff and to be able to ask them questions, I think will be a really great opportunity. And so I'm really looking forward to Thursday as well. And you don't have to really listen to me speak for Thursday, which I think is a nice thing. Okay. And so I do have a few announcements before we actually begin today. And so Friday, I finished grading the midterm. Okay. And so the average on the midterm was 38.5 out of 50, right? And so it was definitely tougher than the first exam, but still within the range that I would like. So I'm going to keep kind of those grades as they are. Okay. And so those grades should be it. And so you should be able to go on Canvas and see what you got on the exam, as well as my feedback for you on that. Okay. I haven't posted the solutions yet, and so that's my bad. And so I should have posted solutions on Friday, but it's kind of slipped my mind up until this point. And so I'm going to scan the solutions in, and then put those in. Okay. And so I'll send an email so that you can see. And so as soon as the solutions are posted, I'll send an email, and then you can check your exam scores against the solutions. And of course, you can let me know if I made any mistakes, and I'd be happy to correct those things. Okay. All right. Am I curving at all this semester? As it is right now, no, because these exams, this exam was lower than the first exam, but the first exam was also pretty high as well. And so I don't expect to be able to I don't expect to curve anything this semester. But of course, we still have the final project left to go. But generally, for these final projects, and those end up usually doing really, really well. And so far, from what I've seen for your final projects, especially in a lot of your progress reports, it looks like they're coming along really, really nicely. And so I think the projects are going to be really, really nice this year. And so I don't expect there to be any kind of curving or grade adjustment at the end. But of course, anything can happen. And if I am going to curve, or if I am going to adjust, I'll let everyone know. But usually I don't really make those decisions until after all of the grades are in, and I kind of see where everyone's at, and then from there I make some adjustments. But until then, I usually don't take a look. But the way things are trending right now, I don't think I'm going to apply any curving. Yeah. Okay. So let me write down guest speaker Thursday. And so usually, for these guest speakers, I personally don't know this speaker, and so it's a bit tough for me to say. But usually they leave a lot of time for questions at the end. So usually like 15-20 minutes for questions. And so definitely come in with questions. I might ask some questions too. Just being interested in learning how he uses ANSYS in industry, and what are some special things to look out for. From that perspective. And so definitely come on Thursday, ask all your questions, and I'm sure he's very happy to answer anything. Okay. Another announcement: SOQs. Okay. Okay. And so the SOQs are up. And by that I mean you can go and fill out the SOQs for this class. Okay, so SOQ stands for Student Opinion Questionnaires. Right? I still don't understand why they just don't call them course evaluations, because that's what they are. So SOQs kind of makes it seem like what does that acronym mean? But those are up. Okay, and those are really important. And so I want everyone in this class to fill out those SOQs. Okay. Because those SOQs are your chance to kind of give me feedback on how this class went for you guys. Okay, so I've spent kind of this whole semester giving you guys feedback on your exams and on your activities and things like that. And so your SOQs are your time to kind of give feedback on that. Okay, and so what I tell my students always for these SOQs is that the only thing I'm looking for in these is just honesty. Okay, and so the way that typically academics work is that things change in the industry landscape, tools change and stuff like that. Usually the academic landscape, we're a little bit slow in adapting to those changes, okay? And I think that's particularly relevant in this class where, a lot of this class is using a very modern engineering tool and then teaching that for you guys, okay? And so for your SOQs, I really want to know, how this class experience was, because I think this class is becoming more and more important as time goes on, okay? And so I really want to make this class something that's a pride of the department. Okay, and so this is the third time I've taught this class. I think I'm going to be the only instructor for this class for the foreseeable future, and so I really want to make this good. Okay, and so please be honest. And I'm not so naive to think that everything went well in this class, because I know it for sure that a lot of things could be improved. And so I have my own reflections on the things that I didn't do well in this class. But I really want to hear from you guys too, to hear what you guys think. Okay, and so please be honest. Please, first of all, please fill it out, because some opinion is better than no opinion always. But when you do fill it out, please be honest and don't be afraid to speak your mind on it. Okay, I've had people curse me out on the SOQs, and I think that's great, because I think that's kind of your raw emotion, that's your raw feelings on the class. And I take those very, very seriously. So please fill them out. Please be honest, because I really want to improve this class. And like I said kind of before too, I tried a lot of new things for this class. I know a lot of them didn't really work out that well, and so please let me know on those SOQs on how I can improve. Okay. All right. And so are there any questions about anything before we get started for today? Okay. All right. So let's go ahead and get rolling. Okay. Oh, deadline for SOQs is this Friday, and so please fill them out by then. Okay. Okay. And so today we're going to be learning about how to do fluid mechanics simulations in ANSYS. Okay. And so this is, I would say that this is traditionally not a very traditional kind of finite element thing, because usually when people think of finite elements, they think of like structures and they think of heat transfer. Because those kind of just naturally are a lot easier to do in finite elements, right? But fluid mechanics for finite elements does exist out there, and it's a real thing. Okay. All right. And so, first let's start with the definition. And so I say this term a lot, and I realize that not everyone kind of knows what it means. But let me define this term, because you'll hear it a lot in industry. Okay. And so fluid mechanics simulation finite elements kind of falls under this category of tools known as CFD. Okay. Okay. And so what CFD stands for, it stands for computational fluid dynamics. Okay, and so all that really means is that we're going to be using computers to solve fluid mechanics problems. Okay, and so you can almost think of like the static structural stuff that we've been doing as SFD, and so that's structural or I should say, no, structure SDD, and so, or C, computational structural dynamics, so CSD. Okay, but CFD for some reason is a ubiquitous term that people use a lot. Okay. All right, and so that's kind of the the main definition, right? And so CFD encompasses a lot more than just finite elements. And so actually, I would say that the more common method for performing CFD is known as finite volume. Okay. And so if you want to learn more about the finite volume method, we have a class on that called EGME 417, and so that's kind of the main topic we go over there. Okay, but finite elements has its own way to doing things too. Okay, and the main difference that I want you guys to remember between doing FEA for fluids versus FEA for solids is in how we CAD up the geometry. Okay. Because I think normally what we're used to when we're doing like finite elements for structures is we build our CAD model for all the solid parts for geometry. Okay. Okay. And so what I mean by that is that usually when we make our CAD models, we usually make them out of the things we're either going to purchase or we're going to machine ourselves. Okay. And so just as an example, I think this example works really well for fluids. Let's say that you're making a CAD model of a pipe. Okay. And so usually when you make a CAD model for the pipe, you make something that looks like this. And so you make a pipe and you have an inner radius and you have an outer radius, okay, where they're separated by the thickness of the pipe. Okay. And you make the pipe go in that direction. Okay. And since you're modeling the pipe, the space that's in the middle here is hollow. And that makes sense, right? Because if you're going to be designing a piping system for like a house or something, and you're going to buy this pipe from like either Home Depot or McMaster or whatever, you're going to get the solid pipe, right? And so if you have a CAD model of the pipe solid itself, that's kind of what makes the most sense. All right, but for CFD, this CAD model actually won't work. Okay. Because the most crucial part that we need for CFD is not the solid, the most crucial part that we're going to need is the fluid, right? Because that's what we're simulating. And so instead of forming a mesh of the solid components of our parts here, if you're going to be doing CFD, you need to make a CAD model of the region where the fluid is going to be. Okay. And so for this pipe example here, instead of making a CAD model of the pipe walls, what you need instead is a CAD model of the interior of the pipe. And so kind of like the cutout of where of the inside. Okay. And so if you think of your CFD CAD models as, I need to model where the fluid is going to be, then that's kind of the mindset that you need to have. Okay. All right. So any questions on this? Okay. All right, and so if you wanted to run a CFD simulation on a pipe, which is what we're going to do later in our example, okay, what you would actually do is the following. All right, and so you would actually make a CAD model of the inside where the fluid goes. Okay. Okay. And so instead of having like a hollow cylinder, which is what we have for the pipe, what you're going to have instead is kind of a solid cylinder, okay, just like that. Okay, and so all of this is filled right here. Okay. And this is the CAD model that we need, because this is what we need to mesh, because that's where our fluid is going to be, right? And so if you want to kind of match this up with the previous page, right? And so the outer radius, or I guess the only radius of this solid cylinder right here, okay, the radius of this solid cylinder has to match with the inner radius of our hollow cylinder. Okay, and so this Ri right here has to be the same in between the both ones. Okay? Right, and so that's how you would make your CAD model for your fluid simulation. Okay, and so remember, it has to be just the region where the fluid is. And so I think this is kind of the part which, you know, if you're kind of used to doing just kind of traditional CAD or structural finite elements, I think this is the part that I think kind of trips people up the most, is that you have to make a fluid, your mesh and your solid of where your fluid's going to be. Okay, I'll give you another example that's often that's used often in practice. Okay? And so let's say that you want to run a CFD simulation on the flow over an airplane. Okay, and so let's say that, you know, you have your airplane here. I'm gonna draw a really crappy airplane. Okay, right, so there's our airplane. Okay, and so you remember, our airplane here is our solid object, and the fluid that we want to simulate is everything that's around it. Okay, and so you don't want to make a CAD model of the airplane. Okay, what you want to make instead is a CAD model of all the air around the airplane. Right, and so it actually looks like this. Right? And so normally you kind of have a big kind of domain like this. Okay, it can be any shape, but for some reason this kind of bullet shape is kind of the most popular. Okay, and in the middle of this domain here, you kind of have a small cutout of where the airplane's supposed to be. Okay. Okay. And then your CAD model is going to consist of everything that's around this airplane cutout. Okay. All right, question. So model the wind tunnel and not the plane. Correct. Yes. And so if you want to run a simulation of, you know, flow in a wind tunnel, you would make your CAD model of all the kind of the empty space within your wind tunnel and just cut out, you know, whatever you're simulating of. Right? So I'll show you some better images once I switch to my laptop. But remember, that's kind of the huge difference in between, you know, running a structural simulation and a fluid one. Okay, that you have to you know, model that. All right, and so the next thing I want to go over just quickly is what equations that we're solving, right? And so for fluid mechanics simulation, the governing equations for this are conservation of mass and momentum in a fluid. Okay, and these equations are very famous, and they are known as the Navier-Stokes equations. Right. So I'm not going to write the equations down. You know, you've probably seen them before. You might have you know, some bad memories of them from your previous classes, but that's basically what's happening under the hood. Okay. And so remember when we were talking about kind of strong forms and weak forms, you know, usually the way that these CFD solvers work is you start with your Navier-Stokes, and so that's like your strong form of the equations, and then you go through the whole process of, you know, multiplying by a weighting function and then performing integration by parts, all on the whole Navier-Stokes. Okay, and so it's a whole ordeal. You know, we could spend 2 lectures on, you know, how to derive the weak form for Navier-Stokes, and it's not a pretty process. Even I don't really want to go through that again, but that's kind of how we do it. Okay, and so for ANSYS, you know, ANSYS actually uses a different program to run CFD. Okay, and so the program that ANSYS runs to run CFD is known as Fluent. Okay, And so we're not going to be running the simulation in ANSYS mechanical, which is kind of what we've done before, right? We will use mechanical to produce the mesh, but beyond that, and as well as some other stuff, but beyond that, we're not going to be using ANSYS mechanical, right? And so I don't quite know the history of this, but it kind of seems like Fluent was kind of its own company before, and then ANSYS just kind of bought them up and just, you know, linked their program with ANSYS, because the interfaces are quite different in between them, right? And so it's not as seamless of a transition. Okay. All right. And so for this tutorial, you know, we're just going to do a very simple pipe flow, and so pipe flow kind of falls under the category of internal flows, right? And so, you know, that's kind of what I'm kind of most familiar with in my own work. But you can do CFD analysis of external flows, like the flow of an airplane. It's just that the setup is going to be a little bit different, but I don't really have that much experience with that, and so I'm going to, you know, not comment on that too much. Okay. All right, and so let's talk material properties. Okay, and so just like we saw in our ANSYS structural simulation, you know, material properties are something that's really important for our simulation. Okay, so for fluids, you know, we need to specify two main properties. Okay, and so one of that is the density of the fluid, right? And so density is just, you know, the mass per unit volume inside the fluid. Okay, and the second thing we have to specify is the viscosity. And so viscosity, if you kind of remember from your fluids class, is kind of a measure of how well the fluid kind of resists motion. Okay, so fluids with high viscosity, like a honey, right? And so those feel really sticky, and it takes a while. If you kind of flip your honey jar upside down, it takes a while for it to come down. Okay, right? And so those are the main properties that we're looking for. Okay, and so it's not too much, but it's you know, you want to make sure that you get these correct. It gets to be a little bit complicated because these properties depend pretty strongly on temperature. Okay, and so, you know, whether you have a glass of, you know, cold water versus a glass of hot water, you know, the density and the viscosity are going to be very different in those conditions. Okay, and so usually you have to make some assumptions about what temperature that your simulation is going to be run at. Okay, and if you have a situation where you expect your fluid to change temperatures a lot, then that's a big consideration that you have to account for. Okay. Okay. Any questions on this? Okay. All right. And so next, I'm going to talk about the types of boundary conditions that you can specify for fluids, and then we'll jump into the program and see how we can set this up. All right. And so there's kind of three types of boundary conditions that I want to go over. And so there's, you know, in reality, there's more, but this is kind of the basics of what you should know in order just to get started with CFD. Okay. All right. And so the first type of boundary condition that we have is a velocity or mass flow boundary conditions. Okay. All right, and so for each of these boundary conditions, I'm going to kind of draw an analogy between this and something that we're familiar with in static structural. Okay, and so our velocity boundary conditions, this is kind of the same thing as applying either like a fixed constraint or a displacement constraint. And so for these types of boundary conditions, we're directly specifying the value of the velocity at a certain surface. Okay. All right. And so just as an example, let's take our pipe flow. Okay. okay, because that's the example that we're going to run. Okay, and so for a pipe, the way that we specify our velocities is we specify the velocity profile, right? And so let's say that we have our cross section like this. Okay, and so let's say that we're going to apply a parabolic velocity profile. And so this is something that we're going to specify on our face, okay? And so for the example that we're going to do, we're going to specify a mass flow rate, okay? And so mass flow rate is just, it's an expression of how much mass passes through a surface, over a given time, okay? But those kind of work in kind of the same way, okay? And so a velocity boundary condition, a mass flow rate boundary conditions, those are the same, okay? And they're the same as kind of like our fixed and displacement constraint, okay? And the reason for that is, if you look at the Navier-Stokes equations, the main thing that we solve for in Navier-Stokes is the velocities, right? And so by specifying a boundary condition on the velocities, that's basically the same as our Dirichlet boundary conditions or our essential boundary conditions, okay? And so those are direct specifications of our solution variables. Okay, so any questions on velocity or mass flow boundary conditions? Okay. All right, and so the next type of boundary condition, actually, is kind of the same as what we've seen before in static structural, are pressure boundary conditions. Okay, and so pressure is a very important quantity for fluid mechanics. It shows up in the Navier-Stokes equations as well. Okay, and the way that you can think of pressure is you can kind of almost think of it as a load. Okay. Right. And so just like, we apply pressure boundary conditions to kind of apply a force to a structure, we can apply pressure boundary conditions to apply a force that's going to drive the flow. Okay. And so this is very common for CFD. Okay. All right. And so, I don't really have much more to comment on that because that's, I think, kind of we all understand kind of what pressure is. Okay. And so typically, what's done. Okay. Typically, whenever you have a CFD simulation, you're going to have fluid that's basically flowing into your domain and then has to flow out, right? And so for a typical pipe, that might look like this, right? What we're essentially going to be simulating is fluid coming in like this, and then fluid is going to flow out, okay? And so our domain is going to be kind of fixed in space, and we're going to be simulating the fluid that goes through it, okay? And so whenever you have a situation like this, you're always going to have some surfaces here that are denoted as like your inlet, okay? And so inlets are places where fluid is coming into your domain, okay? Right? And then on the other side of the domain where fluid is going out, these are known as outlet boundary conditions, okay? Because that's where flow is going out. Okay? And so typically, what's done for these types of simulations, that for your inlets are usually specified as a velocity or mass flow rate. Okay. And then for outlets, typically what's done is we apply a pressure boundary condition here. Okay. Right. And so the reason this is typical, it kind of goes into a lot of the numerics and a lot of the a lot of the computational stuff that I don't think we have time to go over. But intuitively, you can kind of think of it like this. And so usually when you're designing kind of fluid systems, you talk and you're designing like pumps and things like that. One thing that you always consider is what's the back pressure, right? Or in other words, what's the pressure kind of at the back of your fluid mechanical domain, because that's important to know, how much pressure are you working against, right? And so another example might be like you're designing maybe like an aircraft engine or maybe like a rocket nozzle, right? It's important to know, what the pressure is on the back of your device, because that's going to, determine the design of your structure, right? And so this kind of follows the same thing. And so a lot of times, we specify the pressures on the backside of our CFD, okay, where the outlets are, and then from there we specify kind of, all the upstream conditions from that, okay. And so, for outlets, you really only see pressure boundary conditions there. Okay? And so, and I'm not saying it's always this way, but for usually the best results, usually you want to put a pressure boundary condition at your outlets. Okay. For your inlets, it's actually a little bit more flexible, and so more commonly, I would say about 75% of what I've kind of seen just personally. Most people do put a velocity or mass flow rate boundary condition there. Okay. But you can also have pressure. You can also have a pressure inlet boundary condition as well. Okay, it's just not as common. Okay, but of course, your boundary conditions depend on kind of what you already know from the system. Okay, as a lot of you are starting to learn this from your projects, applying the boundary conditions and finding out what the right ones to apply is probably going to be the trickiest part of your simulation, because the boundary conditions have to really reflect, what kinds of realistic situations that your model is going to be under. Okay, and so a lot of times, just kind of based on what you know from the system, maybe the pressure a lot more than the velocity. Okay, and so in those situations, you can apply an inlet pressure, and that's totally fine. Okay, and so both work for the inlet, but for the outlets, you very rarely, I'd say basically almost never see like a velocity boundary condition for the outlet. Okay, and there's very good reasons for that, but it's it's a little bit tough to get into here. Okay, but just know that if you're setting up CFDs, and you have your outlets, just apply a pressure boundary conditions at those. Your inlets are a little bit more flexible, but typically you apply your velocity boundary conditions at your inlets. Okay, so any questions on this so far? Okay, and so the last boundary condition that I'll go over, before we swap over to ANSYS, is the wall boundary conditions. Okay, and so the wall, what I mean by wall boundary conditions are for every exterior surface in your model that's not an inlet or an outlet. Okay, and so depending on the physics of your situation, your wall boundary conditions can be very complex. Okay, but for most situations, or at least the ones that that we'll see, as you're first starting out in CFD, there's really only one option for the wall boundary conditions. Okay, and so the only option is what's called a no slip boundary condition. Okay? And so what that basically says that any fluid that touches your wall, right next to it, the velocity there has to equal 0. Okay, and so that assumes that your walls are totally rigid. Okay, and your fluid can't, it can't pierce through it, and it can't slip on the wall. Okay, and so this is typically what's done. Okay, and so like if you were trying to do a simulation of air over an airplane, right? Typically what you would do is that you would consider your airplane as kind of like a rigid object, and you would say that the air has to stick to the airplane. Okay, and so you apply a no slip boundary condition on that as well. Okay, and so whenever you have a solid surface and that fluid's not going to be passing through it, most of the time you apply a no slip boundary condition on this. Okay. All right. So any questions on this before we swap over to the laptop? Okay. All right. So let me go ahead and close this. Okay. All right, and so let's go over how to set things up in ANSYS, right? And so I have the outlets, I have the outputs here, but let's make, I want to make sure that we get through the whole setup, before we talk about the outputs. Okay, and so here's the example situation that we're going to go over, right? And so we have a simulation where we have a flow in a pipe, okay? And so at the inlet of the pipe, we have a actually relatively very high mass flow rate. And so we have 15 kilograms per second passing through the inlet of this pipe, okay? At the outlet, we have a pressure boundary condition of 100 kilopascals, right? And the fluid that we have going on the inside is water, okay? And so water has a density of almost 1,000 kilograms per meter cubed and a viscosity of 8.9 times 10 to the minus 4 Pascal seconds, okay? And the diameter of this pipe is 20 centimeters. Okay, and so let's jump into ANSYS and let's see how this is set up, okay? And so the first thing that we always do is we have to choose what type of physics that we want to run for this simulation, okay? And so that always starts from here on the analysis systems, okay? And so normally what we do is we choose something like static structural, right? So we've done that a bajillion times this semester, right? We've seen steady state thermal, so that was what we went over last week, right? We have seen topology optimization, and we've seen explicit dynamics, okay? And so to run fluid flow, you have to use one of these, okay? And so it's confusing because they have a million different fluid flow things, okay? I wonder if these are the corpses of all the companies that ANSYS has bought in the past that used to run CFD, okay? And so the one that we want to use and the one that's typically used the most in industry, from what I understand, is Fluent, okay? And so, you can create this the same way. So you can take Fluent and you can drag it over to the workspace here, okay? Right. I'm gonna go ahead and delete this because I already have one, okay? Okay, and then we have this one right here, right? And so from here, it progresses in kind of the same way. And so the first step is you have to load in your geometry, okay? And so we can look at this geometry, right? And so remember, for the CAD model, you have to, you have to load in the CAD model for where the fluid's going to be. Okay, and so for a pipe flow like this, that's going to be of the inside of the pipe. Okay. Right. So design model is starting up. Okay, and so you can see here that we have a CAD model of just a cylinder. Okay. And so this is perfect because that's where the fluid is going to be. Okay. All right. But of course, you don't have to make the geometry here in Design Modeler. You can create your geometry in SolidWorks or whatever other CAD software that you want, and just load it in like normal. Okay. All right. And so the next step that we have to do is we have to mesh. Okay. Right. And so once you upload the geometry, you're going to have to do the mesh. Okay, and so we're going to double click mesh right here, and it's going to actually start up ANSYS Mechanical. Right. All right, and so we're going to give that a couple minutes. Okay, and so what we're going to do in this step is we're going to apply our mesh onto our cylinder. Okay, but we actually need to do one more important step that we haven't done before, which is we need to create what's known as a few named surfaces. Okay. Okay. And so for this simulation, it's just a very basic one, and so I'm just applying just a very basic mesh. Okay. And so you can see here, I didn't even create any meshing objects. The only thing that I did was I changed the element size for this mesh to 1.5 centimeters. Okay. And so you can see here, I have a pretty good mesh density in here. Okay? And so if you measure across the pipe here, there's a lot of elements. Okay. And so typically, you want to have a pretty good mesh like this for fluid flow simulations, because it's fluid flow. Even though typically you're going to be working with linear finite elements, having a good mesh refinement here is good. Okay. All right. And so you can see here for the element order, I picked linear because that actually works a little bit easier in fluid flow more than quadratic. Okay. Okay. Let's see. All right. And so, the main thing that we wanted to accomplish in here is we wanted to create our mesh. Okay. But the other thing that we have to do here is we have to create these things known as named selections. Okay. And so you can see here that I have another section here called named selections, right? And so what this does is it allows us to select certain surfaces in our models and give them a name. Okay. And so this is really important because, because ANSYS Fluent is a totally different program, it needs to be able to identify some of the surfaces, right? And so you'll see that when we get into Fluent, we're not going to be able to select surfaces like this, okay? And so the way Fluent works is that, you need to kind of name the surfaces here in ANSYS Mechanical, and then based on those names, you can then apply boundary conditions on those, okay? All right, so for this one, I already have the name selections created, but let me show you how I created these, okay? Because normally this thing isn't here, okay? And so to create a name surface, you're going to right click on model A3 right here. You're going to go to insert, and then you're going to click on named selection, okay? And so if you read the tooltip here, what it tells you is that it allows you to insert a name selection object to define a grouping of geometries or meshing entities, okay? All right. And so the main way that we're going to do this is we're going to name our surface. So actually, let me go ahead and delete this one right here, and I'll show you how to create this named selection. Okay. All right. So let's go ahead and right click Model A3 and click Name Selection. Okay. And I want to create a name selection for the wall, right? And so the wall being kind of the outer surface, because that's that's where we're going to apply our no slip boundary condition, right? All right. And so you can see here under selection, you can see here that on the bottom left, we can select our geometry for this, okay? And so we want to make sure that we're on face mode, okay? And so we can go ahead and select the outer surface of the cylinder here, okay? And then we can go ahead and hit apply, okay? And then from here, and so you can see after we've hit apply, now the surface that we've labeled here is highlighted in red, okay? And so what we can do from here is we can name it, okay? And so just like we always do, we can right click this and we can hit rename, or we can just simply hit A2 or F2, okay? And we can name this to wall, okay? All right. And so that's going to be important because, we need to, specify, we're going to use these name surfaces to specify our boundary conditions, okay? And so you can see here, I've created one surface called the wall for the lateral surface. I've created one name selection for the inlet, and so that's where we're going to place our inlet boundary condition. And I've also created a surface, a name for the outlet, okay? And so that's where we're going to put our outlet boundary condition. Okay. All right. And so when you're doing this, make sure you pick useful names, and so don't pick, Facey McFace, right? And so that's usually not helpful. And so you want to pick a name that's going to tell you, what type of boundary condition that you're going to apply there. All right. So any questions on this? Okay. And so now that we've applied our mesh and we created our name selections, we're all done with mechanical. All right. So we can go ahead and close mechanical. Okay. All right. And so when you return to Workbench, like what you should notice here is that the mesh has this kind of lightning bolt next to it. Okay. And so all that means that you just have to update it. Okay. And so before you go into ANSYS Fluent, let's go ahead and update our meshing object. Okay. And so to do that, you can just simply right click on the mesh, and then you're going to click on this button for update. Okay. It's going to take a little bit of time. Please don't crash. Okay, good. All right. And so once the mesh has this little green check mark next to it, we're ready to jump into Fluent. Okay. And so you can see the next step in our process here is setup. And so let's go ahead and double click that. Okay. So yes. All right. And so you can see in the bottom left here, we're starting a new program called Fluent. Okay. All right. And so if you're running this for the first time in a while, you will probably have this Fluent launcher come up. Okay. Let's see. Okay. And so all of these look good. Okay. And so, if these are your default settings, these are usually good. So you can go ahead and click start. Okay. And then Fluent is now going to start up. All right. Okay, and so you can allow access for Fluent to steal all your personal information. Okay. Yes. I'm okay with our ANSYS overlords. That is fine. Okay. So you can see things are still kind of starting up. Okay, and so I've already run the simulation, and so you can kind of see the results here, but I'll kind of walk you through the process of how to do everything. Okay. All right, and so if you're running this kind of alongside me, you might see just a gray cylinder here. Okay, and so that's good because then that shows you that your geometry attached correctly. Okay, and so you can see right away, this interface is very different, right? And so very clearly this program was developed by a different company other than ANSYS, and then ANSYS bought them in true capitalism and then took over their company, and then now they're part of ANSYS. Okay, all right. But very similar to ANSYS, we're gonna our primary way of kind of organizing things is going to be everything here on the left. Okay. And so just like we typically do in ANSYS Mechanical, we're kind of just going to run down this list right here and kind of just take each of these steps kind of one by one. Right? All right, and so the first thing that we're going to do is we're going to click this plus arrow next to models, okay? And so from here, you're going to be able to set, a lot of different settings for your simulation, okay? And so when you first kind of open this, it might seem very overwhelming because there's a lot of stuff here that you can do, okay? So you can do things like you can do multi-phase flow, you can do heat, okay? You can do species evolution, which is like a mass transport kind of thing, right? You can have acoustics, right? And so it's a lot of stuff. And so if you're just interested in running just a pure fluids type of simulation, which is what we're doing here, you can ignore most of this stuff, okay? And so the only thing that we have to specify here is our model for the viscosity, okay? Or in other words, our model for the turbulence, okay? Because the thing is, if you're running CFD on fluid flow, one thing that can happen a lot is your flow can go turbulent, right? And how your simulation handles the turbulence is something that's really, really important, but it's also something we really, really don't have time to go over, okay? And so for this particular problem, what we're going to assume is that our flow is going to remain laminar, okay? Okay. And so what you're going to do is under models, you're going to double click on this setting called viscous, okay? As you can see here that we have a lot of settings for how we can specify how the viscosity in our simulation behaves. Okay, and so I think the default here is to choose one of these settings here. Okay, and so believe it or not, everything that I'm highlighting of my mouse here, these are all different ways to model turbulence. Okay, and so if you've ever been in any of my fluids classes before, you probably heard me say that turbulence is very fascinating, but we also don't understand anything about it, okay? And so, despite, many years of research, turbulence is still kind of a mystery to us, right? And so everyone and their mom right now is like trying to find out what are the best ways to model turbulence, and they all kind of don't really work that well, okay? And so, if you want to model turbulence, you have to pick a good model here. And so usually, these models are very kind of case specific. And so, I'm not really going to get into all this stuff. But for now, we're going to assume that, we're just going to work with laminar flow. And so we're just going to work with kind of just straight up Navier-Stokes. And so the way you do that is you pick this laminar button right here. Okay, make sure that one's selected and you click OK. Okay. All right. And so that's our turbulence model. Okay. All right. And so the next thing that we need to do is we need to specify our fluid properties, okay? And the way that we're going to do that is under materials. Okay? And so you're going to click on this plus arrow right here next to materials, okay? And you can see here that I have two entries here, one for fluid and one for solid. Okay? And so if you're opening up ANSYS Fluent for the very first time, probably the only entry that you'll have here is air, okay? And so if you want to run a simulation with air, that's great. Okay, that's kind of like our structural steel of fluids. Okay, but for this simulation, we want to run a simulation with water. Okay, and so probably what you're going to have to do is you're going to have to create a new material here for water. Okay, and so you're going to right click on fluid right here and click new. Okay, and then if you click that, then you should have a new window that opens up right here. Okay, and so in this window, what you can do is you can specify first of all, the name for your fluid. Okay, and so let's say that we want to specify the properties of water. Okay, I already have water, so I'll call this water 2. Okay, water 2, the sequel. Okay, And you can see here that the main things that we have to specify here is the density as well as the viscosity. Okay. Okay. All right. And so, you know, if we make this water 2, okay. And so for the density, you have to select, you know, first of all, you have to select the units here, okay, or make sure that you're in the right units. And so for in this case, we're going to specify the density in kilograms per meters cubed, okay. And so this has a value of 999, right? And then the viscosity is given to you in kilograms per meter second. And so I think this is slightly different. Or no, it's the same. It's the same units that what we had before, okay. And so the viscosity for this is going to be 0.00089 or 8.9 times 10 to the minus 4. Okay. Okay. And so I already have this, and so I'm just going to just close this, but you know, make sure that you input the correct fluid properties for what you want to simulate. Okay. All right, question. So can we change the acceleration due to gravity in this program? Say we want to run a CFD sim for Mars or some other planet. Can that be done? Oh, absolutely. Yes. And so I think the where you set that might be somewhere here. And so I've never done it because I've never done a simulation for that. But you know, there's usually a setting there for you know, what you can set the gravity to be. Actually, you know, for a lot of simulations, a lot of times you ignore gravity because you know, a lot of times it doesn't make that big an impact. But you know, if you do want to include gravity, you can certainly do that, and then you can input the acceleration due to gravity for you know, whatever you want to do. Yeah. Okay. And so now that we've you know, we've created this new material property called water, now we have to actually specify this material property for our simulation. Okay. All right. And so to do that, you're going to open up this tab right here called Cell Zone Conditions. Okay. And under here, you're going to have something called fluid. Okay. Right. And so in order to specify this as water, you're going to double click this. Okay. And then for this material here, you're going to select water. Okay. Right. So you want to make sure that you're using the correct fluid for this. Okay. All right. Okay. All right. And so that's how we create a new material property, and that's how we apply it. Right? So any questions on this so far? Yeah, you can. Yeah, you can try. You know, for those of you who are in my cardiovascular class, you can try running your simulation in ANSYS Fluent as well, and compare that to vascular. Yeah. Okay. And so now that we've supplied the correct fluid properties, now it's time to apply the boundary conditions. Okay. All right. And so in order to apply the boundary conditions, we have to go to this tab here called you know, boundary conditions here. Okay. Right. And so you can see here that we have an entry here, you know, for each of the different name surfaces. Okay. And so that's because I've kind of already set the simulation up. Right. Okay. And so, you know, the way we're going to do this is we're going to, you know, right click on our name surface here. Okay. Okay. And then from here, we're going to go to type. Okay. And then from here, we can select the type of boundary condition that we want. Right. And so for our inlet, if we go back to our, you know, example specifications, we want to specify a mass flow for the inlet. Okay. And so for our inlet here, you want to make sure that we're on mass flow inlet. Okay. And so after you do that, you can go ahead and bring up this, you know, this new window here. Okay. And our mass flow rate for the inlet, you know, is going to be 15 kilograms per second. Okay. All right. And so the last thing you have to set here is you have to set the direction for your velocities. Okay. So this is really important because this is going to determine whether your flow goes into your domain or out. Okay. And so, you know, in order for our flow to go into the domain, you know, we need to make sure that the flow goes in the minus z direction, which is what we see right here. Okay. And so in order to make sure that the flow goes in the minus z, you know, we want to make sure that the x component is 0, the y component is 0, and the z component is -1. Okay. And so this is very similar to how we apply our boundary conditions in, you know, typical ANSYS mechanical. It's just that now, you know, we're doing it for fluids. Okay. And so you want to make sure that direction is correct. Okay. So any questions on this so far? Okay. All right, and so let's go ahead and apply that. And so that's going to be our inlet boundary condition. Okay. Next, we're going to set our outlet, right? And for our outlet boundary condition, we're just going to set a pressure outlet, right? And so remember, if you're running these kinds of simulations, typically you pick a pressure for the outlet boundary conditions. Okay, so let's go ahead and click that. Okay, a new window is going to pop up, and this is going to allow us to set our pressure, right? And so the only thing you have to do here is you have to select the pressure, which in this case is going to be given in pascals, right? And so you're going to set a pressure of 100,000 kilopascals, right? And so that's exactly what we have here, okay? Or sorry, we have 100 kilopascals, and so that's going to be 100,000 regular pascals, right? And so we apply that here. You can keep everything here the same way, okay? And so you can go ahead and hit apply, hit close, okay? And then last here we have our wall boundary condition, okay? And you can see here that ANSYS has a special type of wall boundary condition, which is for no slip, okay? And so when you go to the wall right here, you want to make sure that you pick a wall type, okay? And so that basically makes sure that you're going to have no slip at your walls, okay? Okay, and so that's all the boundary conditions. Yep, right. And so we're basically done with the setup, right? And so we've applied our fluid properties, we've applied our mesh, we applied our boundary condition, and so the last thing we have to do now is just initialize the simulation and run it. Okay. All right. And so we can ignore most of these other settings here because they're kind of more advanced for another day. Okay. But to run your simulation, you're going to go to the next kind of section here on the outline view, which is solution. Okay. And you're going to double click on initialization here. Okay. And then you can go ahead and click initialize. Okay. And so here, you have a couple of options. You can do a hybrid initialization or a standard. Okay. And so most of the time you want to do a hybrid initialization because that's going to give you, a little bit better results. Okay. Right. And so you notice that after you click initialize, then you're going to have some stuff here, that's happening at the bottom. Okay. And what you should notice here is that after you click initialize, that this number here in the second column, it's steadily getting smaller and smaller until it reaches a point where it kind of can't get any smaller than this. Okay. And so that's good. And so what that basically tells you is that for your initial field, then the error in that initial field is getting lower and lower. Okay. And so you want this number to keep going down because it represents the error or the residual in your initial solution field. Okay. Okay. All right, and so now that we've finished with the initialization, we're now ready to solve, okay? And so the way that we're going to solve is we're going to go to this very aptly named button called Run Calculation, okay? Okay. All right, so question, so we don't have to worry about the number of cores and killing our computer. If for anything that you're running for the trial, the student version of ANSYS, you don't have to worry about that because it basically doesn't let you run any meshes that are too high, and so you can just go ahead and run it on your computer. So it's usually not an issue. Okay, and so let's go ahead and double click Run Calculation. Okay, right, and you can see here that we are presented with a lot of settings. Okay, all right, and so here there's a lot of settings and a lot that we can talk about. Okay. A question. So mine wouldn't let me do more than 4. Kept getting licensing errors. Oh yes, yeah. So yeah, probably with the student license, it probably won't let you use too many cores. And so I think for this one, I'm just running on 1 core actually. And so for that, this is perfectly fine. But yeah, if you have a multi-core system, you can run it on multiple cores if you want. But for this, 1 core should be plenty. Even on potato computers, I think it should be fine. Yeah. Okay. And so the only setting here that we really have to worry about is the number of iterations that we want to solve. Okay. And so in this case, we just have a steady simulation, and so we have kind of an inlet condition coming in and an outlet pressure, and none of those are changing with time. And so for steady simulations like this, 10 iterations is totally fine. Okay. And so it'll get us our solution pretty quickly. Okay. But if you're running an unsteady simulation, you might want to bump this up a little bit more. Okay. Right. And so, everything else here, I'm just going to leave it as the defaults just because, we only have 15 minutes. And I do want to show you the results. Okay. And so let's go ahead and click calculate. Okay. And so after you click calculate, a bunch of stuff is going to, start appearing here in the bottom. Okay. And since this was a very light simulation with a very modest mesh, it just doesn't take that much time at all. Okay. And so you should get a notification here that says calculation complete. Okay. So you're going to hit OK. Right. And so now that the calculations are complete, we're ready to view the results. Okay. Okay. So any questions on this so far? Okay. All right. So let's go ahead and view the results. Okay. And so now that we're ready to view the results, we're going to go ahead and move down to this bottom section here. Okay. And so first thing we want to see is we want to see kind of a graphical representation of our results. Okay. Okay. And so first thing we're going to do is we're going to add a contour. Okay. And so you're going to go to results under graphics, go to contour. You go ahead and click new. Okay. Right. And so a contour is basically kind of a color plot of your results. Right. And so, this is kind of intuitively what we've kind of seen from our results in ANSYS Mechanical. Right. And so we wanted to see things like the deformation field or the or the stress equivalent stress field. Basically what we're viewing is a color contour of the results. Okay, and so we can do the same thing here for for fluid. Okay, and so let's say that we want to view a color contour of the pressure. Okay, and so that's the first thing that we can see. Okay, I'll show you all the other ones later, but first let's go over pressure. Okay. And so to view the results, you want to make sure that you're viewing the pressure here, okay? And you also want to select all the surfaces in this list, okay? Because we want to view the surfaces on all of those surfaces, okay? All right. And so once you've selected the pressure here and you've selected all the surfaces from this list, we can go ahead and click Save / Display, okay? And you do that, you can now view your results, okay? Right, and so what you're viewing here is the pressure distribution inside your cylinder, okay? And you can see here, our pressure distribution, even though it goes down, right? It's still relatively the same, right? And so if you look at this bar right here, we see, whoa, that's kind of freaky, okay? And so you can see here that, as we go from red to blue, we go from 1 × 10⁵ to 1 × 10⁵, right? And so there's changes that's going on, but it's very small because we have basically just a very, very simple pipe here, and so we don't really have that much pressure drop. Okay. But if you are running a fluid simulation, this is typically what you should see, right? Because if you remember, the left side of our pipe here, this was our inlet, and then the right side was the outlet, right? And so what you should see is that you should see a drop in pressure from the inlet to the outlets. Because that pressure drop is usually what's going to be driving your flow, right? And so you have an inlet pressure and an outlet pressure, right? And so flow is going to go from high pressure to low pressure, right? And so is that exactly the same thing as thermal, right? And so for thermal simulations, heat's going to go from high temperature to low temperature. Fluids are exactly the same way, right? So fluids are going to go, from high pressure to low pressure. Okay. All right, and so that's the pressure contour. Next thing we can view is the velocity, okay? And so on this color contour settings here, I'm going to click on velocity, okay? And I'm going to click display, right? And so now what you're seeing here is the velocity contour of our solution, okay? All right, and so you can see here the velocity contour looks very different, right? And so you can see here we actually have some variation too, right? And so our velocity has a minimum value of 0 and a maximum value of 0.481 meters per second, okay? All right, so what are we looking at here, right? And so you can see the entire outer surface of the cylinder here is blue, okay? And that makes sense, right? And we want to see that because remember what we assigned for this outer surface here was a no-slip boundary condition, right? And so all that means that we're saying that the velocity on the outer surface here has to go to 0, right? And so that's good, right? And so we don't have any flow leaking out the sides of our tube, right? So we have kind of a nice airtight one. On the other hand, for the inlets and the outlets, you can see here that we have a lot of velocity magnitude, okay? In particular, you can see that we have a very rapid change, okay? Right, and so if you go from kind of the outer surface in, you can see that the color changes from blue to light blue, to green, to yellow, to red, and red kind of takes up the majority of the space. Okay, and so what that tells you is that most of the velocity magnitudes on this surface is going to be high, right? And so the red here corresponds to a velocity magnitude of 0.481 meters per second. Okay, and so for most of the surface here, we have that as the case. Okay, right, and so our outlet looks relatively the same, right? And so our inlets and our outlets, this case, from kind of an interesting point of view is not all that interesting because it's just a simple pipe. Okay, but it's good as kind of like a sanity check, right? And so before you run kind of very fluid flow and kind of very complex systems, you have to start small, right? And so this is kind of our starting small kind of place, right? All right, and so that's the velocity. And there's one more thing that I want to show you guys, and that is the wall shear stress. Okay. Right. So let's go to wall flux. Okay. Right. And so I want to show you this wall shear stress because it's it's something that I've worked with a lot personally in my own work. Okay. So let's go ahead and display this. Okay. And so what the wall shear stress is this is kind of the viscous stress that the fluid is imparting on the wall. Right. So remember what we talked about before, that viscosity. This flow is viscous, right? And so it has a decent amount of viscosity. And so what that means is that, the fluid is going to kind of drag along the surface, right? And so just like when you rub your hands together, you're having, there's some friction force that occurs there because, you have, friction that occurs between your hands, right? Whenever fluid flows past the surface, there's going to be some frictional forces there as well, right? And so that's due to the viscosity of the fluid. And so what we're viewing here in the wall shear stress is the, this is the, basically the viscous shear stress that the fluid is imparting on the wall, okay? And so this has a lot of applications for, the kind of work that I do, which is, blood flow, right? And so, for blood flow, this viscous shear stress is something that's really important to quantify, okay? And in fact, it's one of the main reasons why we run CFT for this, okay? All right, and so the last thing I want to show you is how to obtain the path lines, okay? And so path lines are really cool because that basically shows you, the path where your velocity is going, okay? So for this particular case, it's not going to be that interesting because it's just flowing a pipe, but let's kind of view it anyway, right? All right, so let's go ahead and right-click path lines, okay? Let's go ahead and create a new one, okay? And so here we have our path lines object, okay? And so, the only thing that we have to select here is we have to select which surface that we want to release these path lines from, okay? And so for the path lines, you can almost think of it as, we're releasing kind of these marked particles into our flow, and our particles are just going to flow throughout the domain, okay? And so in this case, let's go ahead and select the inlet, okay? Because that's where our flow is coming in, okay? So let's go ahead and select that, right? And so what you're viewing here are the path lines for this simulation, okay? And so you can see here that the flow is starting at the inlet right here, right? And so if we release kind of a bunch of particles, and so those particles are just going to run, in a straight line through the tube and then go out, okay? And so, again, this isn't super interesting because the flow just goes in a straight line. But if you have kind of a piping system where, you have pipes that come off here, this visualization usually looks pretty cool. Right, because then what that tells you is that it tells you which paths that the particles are going to go, and you can kind of exactly see where everything is headed. Okay. Okay. So any final questions on any of this? Okay. All right, and so that kind of concludes kind of this this very introductory tutorial on fluid mechanics in ANSYS. And so I will say that we just barely kind of scratched the surface, but at least this shows you kind of at least how to set these things up, how you mesh these things, how you create the name surfaces, and just kind of where a lot of the main buttons are, right? And so of course this tutorial is not meant to be expansive, but it's meant to just kind of get your feet wet to if you want to explore this further, you can have a good foundation here to start. Okay. All right. And so, before we go today, since I don't know how much time we're going to have on Thursday with the guest speaker, I just want to take a moment just to say, thank you guys for being part of this class. I know, with the pandemic and everything, taking school right now sucks, right? And so, and I understand that, right? So being a student right now and having to take everything from your home with all kind of the difficulties with the virtual instruction, like it sucks. But throughout this whole thing, everyone in this class, I can proudly say that everyone stuck with it, as best as we could, right? And so, as you guys made this class, much, way more enjoyable than it had to be, right? And so, I know with the virtual instruction and debugging things in ANSYS and with the homeworks and everything, it was tough, and it kind of, it sucked, and and I know I made a lot of mistakes along the way too. So, I just want to take a moment to say thank you guys for all the hard work you put in this class. I just want to thank you guys for your patience with me and working through all that stuff. And in case I don't get a chance to on Thursday, I just want to say, everyone, I wish you guys have a great summer. For the seniors that are graduating, I want to say congratulations. You guys made it. Legitimately, you guys made it. You guys deserve, all the accolades and all the respect in the world. And so you can say that. So I can really say that I'm really proud of you guys. I can say that, I really love you guys. I've always loved being your instructor. I've always loved, being a part of your journey. And so, just want to say congratulations, and I wish you guys all the best. All right. I will be at graduation, yes, and so I will be there, and so I'll definitely see you guys there as well. Yep. All right, so thank you guys. I guess I'll sign off for and I'll see you. I'll be there Thursday too, but I don't know what the plan for the guest speaker is as well, and so I'll see you then. But I did want to take a moment just say thank you to everyone, and so best of luck on your finals. We still have the final project in this class, so definitely reach out to me if you're having trouble with that. And I'll see you guys at graduation, and even beyond that, if I can be a resource for you guys outside of this class, either to help you out with your professional life or to be a reference or anything like that, please, I'd be more than happy to do that. So please don't hesitate to do that, and I'm always going to be here for you guys. So thank you guys, one last time, and I'll see you guys around.
So are we done here?
Yes, we're done. Yeah.
Can I ask you a question about getting videos from that 417